So for this question, we're asked to draw the shear and moment diagrams for the cantilever beam and to determine the shear and moment throughout the beam as functions of x. So it's basically asking us to use the equation method to draw both the shear force and bending moment diagrams. So no matter what method we were going to use anyway, we need to start by determining the reactions. So I've drawn over here a partial free body diagram. All I've done is transfer across all the loads that we can see. And what I need to do is replace the fixed joint here with their equivalent reactions. So we know that a fixed joint is going to react with a horizontal, which I'll call AX, vertical, which I'll call AY, and moment, which I'll put in as MA. So in other words, I'm going to call this point down here A. Alright, so we need to go ahead and apply our equilibrium equations to figure out MA, AX, and AY. And in order to do that, I'm going to need to simplify this distributed load to be a point load applied through the centroid. So let me scroll down here for a second where I've drawn my free body diagram as well. And in order to find the reactions, as I said, I'm going to replace this with just a point load. So this is a rectangle that you can see. So we would expect the centroid to sit somewhere here, and I'm going to apply my point load through it. We can work out the size of the point load. It's going to be 30 kilonewtons per meter multiplied by the number of meters over which it acts. And going back up here, we can see it's over 1.8 meters. So this works out to be 54 kilonewtons. I should also draw that in. So we said it was 1.8 meters in here, but this is going to be acting through the center. So on either side, it should be 0.9. And I'll pop this in as well. This distance in here was 1.2. Alright, so let's go ahead and find what the reactions are. So I'll start by summing my moments about point A, this one in here. So I'm going to have the moment reaction, MA I've called it, and it's been drawn anti-clockwise, so it's going to go in as positive. AX and AY act through at point A, so they're not going to be in the equation. I can then take my point load of 54 kilonewtons, and it's acting at a distance of 0.9 meters, and it's going to try and rotate this thing clockwise so it's negative. So that deals with the distributed load. We've then got the 50 kilonewtons at a distance of 1.8 meters, again trying to rotate clockwise. We've got the 40 kilonewtons at the full length of the beam, which is 3 meters, again trying to rotate clockwise. And finally our couple on the end, which is clockwise as well. So simplifying this, we find out that the moment at the wall is equivalent to 458.6 kilonewton meters. Alright, so I also need to determine the other two reactions, so AX and AY. AX is really easy because if you sum forces in the x direction, it's the only thing, so it's going to come out to 0. Let me pop this one in. And AY we can determine as well by summing forces in the y direction. So we're going to have AY going up. We've got the point force, which is the simplification of the distributed load of 54 going down. We've got 50 going down. We've got 40 going down. So AY must be equal to 144 kilonewtons. Alright, so I've gone ahead and put each of these reactions back onto my original diagram. So now what I need to do is start developing the equations that describe the shear and the moment through each of the sections. Now I need to make a new section every time I have a change in the loading across my beam. So I called this point on the end here A. Okay, and we can see that from A all the way until we hit this force here, we've got consistent loading. It's just a distributed load. So I'm going to need to make a new section when I hit this point, which I'll call B. And if we keep going along, we can see there's consistent loading here, nothing changes. In fact, there's nothing at all. So on the end here is going to be point C. So I'm going to need an equation that describes stuff through this section, AB, and a second set that describe what's happening between B and C. So let's start by looking at section AB, and in order to do this we need to cut between those 2 points. So when we perform a cut through here, we need to draw either the left or the right hand side. I'm going to redraw the left hand side of the free body diagram. Alright, so we've cut through here. I probably should have cut it off a little bit earlier, but anyway, we've performed a cut through here. I've redrawn this bit, which is this bit here. Oh, I've missed off, sorry, the moment reaction that we had on the end here of 358.6. And what I need to do is determine the internal shear and moment at this cut point. Okay, now we need to make sure that we draw shear downwards and the moment anti-clockwise because we've taken the left-hand side of the diagram. This is so that we get the sign convention correct. If you're unsure on this, go back to the recap video. I described why we were doing it in there. Alright, so the other things I need to label is the length of the beam. So I've decided to cut this off at what I'm going to call a length of X. Okay, the X comes about because we're being told that we're measuring X from the left hand side here, and so we're going to cut the beam at some point, measure V and M, and it's going to be for that generic value X, the length of the beam. So in order to work out this V and M value, again I'm going to need to simplify this distributed load. So I'm going to make it a point load acting through the centroid of my rectangle. And the size of it is going to be the 30 kilonewtons per meter multiplied by the number of meters, which is X. So let's go ahead now and work out V and M. So I need to make sure I'm in equilibrium, which means the sum of the forces in the y direction have to be 0. I've got 144 going up. I've got the 30x going down from the point load of the distributed load. And I've got minus V, has to be 0. So getting V on its own, we end up with that. Alright, so now we need to get the moment M, and I can get this by summing moments about any point on this beam, but usually the easiest place to sum is at the cut point, so here on the end. This is because you've got your shear force acting through it, so it's not going to end up in the equation, and it saves you then having to substitute this into whatever equation you develop for the moment. So, summing about this cut point, V is out, so we then have our moment M, which is drawn anti-clockwise, so it's going to go in as positive. We've then got the 30x of the point force, and I forgot to draw it in, but we know that this is going to be acting halfway along. Okay, because it's the center of the rectangle. So the distance from the cut point back to this is 0.5x, and the direction is going to be anti-clockwise, so it's positive. We've got the 144 acting at the distance of x meters. And this is going to try and rotate clockwise, so it's negative. And finally we have our couple on the end of 458.6, which is drawn anti-clockwise, so it's positive. So we need to rearrange this to get M on its own, and when you go ahead and do that, it comes out to be negative 15x squared plus 144x minus 458.6. So this equation describes shear, and this equation describes the moment through the section AB. So what I want to do now is just put some values around what x values that means it's applicable for. So let's go ahead and do that. So remember, we're measuring x from this end. Or let's do it off this diagram. We're measuring from this end, and this is A, this is B, and this is C. So it's going to be section AB is from x is equal to 0 all the way up until x is equal to the 1.8 meters. Okay, so 0, x, 1.8 meters is where these equations can be plotted for. So that's one section done. Now we need to go through and repeat this for the other section. So now we need to cut between section B and C, so through here. So once we cut, we need to redraw either the left or the right hand side of the free body diagram. I'm going to choose to draw the left hand side again. So let's go ahead and do that. So we've still got the distributed load acting across the beam. We know that we have that point load of 50 kilonewtons as well. And otherwise we've just got these reactions on the end that we need to put in. And this one here was 30 kilonewtons per meter. Alright, so what we need to determine is the internal loads on the beam, and because we've taken the left hand side, we need to make sure that we draw shear downwards and the moment anti-clockwise. Okay, these are what we need to go ahead and find out. Now, in order to do this, again, we need to simplify the distributed load. We know that this time we've taken the entire distributed load, which has a length of 1.8 meters. And the other thing I should mark in here is that where we've cut the beam, again, we're going to call it a length of X. So we cut it off at this length X and we determine V and M for that case. So the distributed load, again, can be a point load through the center. It's going to be 30 kilonewtons per meter by the 1.8 meters, which we said before was 54 kilonewtons. And we know that this is applied at the halfway point of the rectangle. So it's going to be as if we had 0.9 meters on either side. Okay, so let's go ahead and work out V and M. I'll start by summing forces in the y direction to be equal to 0. So we're going to have 144 up minus the 54 going down from the distributed load. We've got the 50 going down as well, and we have V going down. So rearranging to have our shear force on its own, it actually just comes to be 40. So now we need to get the moment, and I'm going to sum about the cut point. So we have M, which is drawn anti-clockwise, so it's positive. V acts through the point, so it's not going to be included. We've then got the 50 kilonewtons acting at a distance in here, which we can work out. It's this little bit. So if this is X and this is 1.8, this distance is going to be the difference, which is X minus 1.8. So that needs to go in here. And this is going to try and rotate anti-clockwise, so it's positive. We've then got the 54, which is acting at a distance in here of, it's going to be this X minus 1.8 plus the extra 0.9. Okay, this is going to try and rotate us anti-clockwise, so it's going to be positive. We've got the 144, which is going to be acting at a distance of X meters, the full length in here. And it's going to try and rotate clockwise, so it's negative. And finally, we have the 458.6 on the end, which is drawn anti-clockwise, so it's positive. So if you expand out all these brackets and put things together, and put M on one side of the equation on its own, all it becomes is 40x minus 320 for the bending moment. Alright, so again, these two equations that we've just developed are only applicable for the section that we've calculated them for, so between B and C. So we should put some values of x around where that makes the equations valid for. So going back up, we're looking for what x equals between points B and point C. So when we get to point B, x here is going to be equal to 1.8, and then we need to go an additional 1.2 meters to get to C. So that means that section BC is from 1.8 meters to 3 meters. Cool. Okay, so the last step is just to now draw the shear force and bending moment diagrams from these equations. So I've summarized what we've found so far, which is for section AB, which is between x's 0 and 1.8, we get these equations. For section BC, which is between 1.8 and 3 meters, we get these two equations. So I'm going to start with drawing the shear force diagram, and all of my equations are in kilonewtons, since that was the units of everything on the diagram. So, starting at x equals 0 and going up to x equals 1.8, we need to use this equation to plot. So the equation is 144 minus 30x. So if we figure out what it is at x equals 0, subbing that in, x is 0, we're going to get the answer of 144. We know that this has to start at 0, so it must then shoot straight up to 144 kilonewtons. We can then work out what it's going to be at 1.8 meters by substituting 1.8 in for x, and it ends up being 90. And this is just going to be a straight line with a negative gradient, and it's negative 30. And of course, feel free to chuck this in a calculator if you're unsure of what the shape of the graph ends up looking like. So we said that we could work it out. It's 144 take 30 by 1.8, and this actually comes out to be 90. Alright, so that's up to 1.8. We need to go ahead and use the next equation in order to work out what's happening between 1.8 and 3. And we can see here that we've got an equation that a shear is equal to 40, and it's basically independent of x. So that means that it's going to stay constant between 1.8 and 3 at 40. So we must have a step change here from 90 to 40, which kind of makes sense because that's the point where we had a point force applied to the beam. And then we know that we have to end at 0. So again, there must be a step change at the end to take us back to 0. So that's what the shear force diagram looks like for this question. So now we can go ahead and do the same sort of thing with the bending moment diagram. This time the units of everything are going to be in kilonewton meters. So let me draw our line again. Alright, so this time between 0 and 1.8 meters, we need to apply this equation, the moment version. Now this one's very difficult, I think, to picture what it's going to look like because it's going to be a parabola. It's got an x squared term. So I would highly recommend plotting this one in your calculator or Wolfram Alpha or something like that to see what it looks like over this, this domain. So if you go ahead and do it, what it looks like is it's going to go straight down to negative 458.6, which is easy enough to determine if you substitute x equals 0 in here. And the shape of it kind of looks like this, all the way over to 1.8 meters. So at that point, this equation cuts off, and we need to use the second one in order to draw the last bit from 1.8 up to 3 meters. So this one is a straight line. It's got the mx plus c form to it. And again, I would definitely recommend putting this in a calculator to see what it looks like. It ends up just looking like this between 1.8 and 3 meters. And then if you put 3 meters in here, you end up figuring out that it ends at about negative 200. The units again, kilonewton meters. So there must be a step change at the end to take it back to 0, and that's caused by the couple that we had on the end. Alright, so that's the two diagrams that we were looking for. Let me just scroll down and show you what they look like if you were to plot them in some software. So for example, MATLAB. So again, we have them starting at and ending at 0 on both ends here. Shoot straight up, has that diagonal line going down, step change flat at 40, and then down again, which is what we plotted. For this bending moment diagram, it's hard to see, but again, it starts at 0 and it shoots straight down. We have part of the parabola in this zone. It then transitions to the straight line after 1.8 meters and has the step change back to 0 at the end as well. So that's all there is for this question, and see you in another video.